Okay, so here we're looking at the domain of this function. So this is not necessarily new information. We've actually kind of talked about this domain, but it's the approach that we're going to take. And this is going to be a theme that we'll see on and off. I mean, not every single time, but on and off throughout this class is we want to elevate the way that we look at some of these topics, right? So it's not just about, oh yeah, I learned that in another class. Here's kind of the quick and easy answer. It's really understanding the fundamentals that go into why we have a quick and easy answer, right? So we want to dig a little deeper than maybe we're used to in a class like this. So when we look at this, we're aware of we're aware of the fact that we can take our function 1 over x, we can set the denominator equal to 0, right? And say that our domain is the set of all real numbers excluding 0. So you could say something like domain is all the set of all x belonging to real numbers, so all x's in the set of real numbers, excluding 0, and I will write that underneath. Let me say that. All x's in the set that are not equal to 0. Okay, that's a very shorthand way of writing it. We'll use more notation as we move forward. You could also, though, say this in interval notation, and that's a pretty common approach as well, right? We could also say, or negative infinity to 0, union 0 to infinity, right? And those are all open intervals because that 0.0 is not included. But I think the question that kind of drives this is why, right? Why do we do this process right here? Why do we set it equal to 0? Some people write not equal to 0. I think that just depends on who taught you. It's really a preference thing, but why do we do that? Some of the reasoning and some of kind of the rationale behind it is this, and it is kind of working hand in hand between the two kind of approaches. So we don't exclude this process right here. We still are very aware of what makes my denominator 0, but then we justify it. It's like we don't stop there. So what would happen if we were to pick some x values, and we're more used to writing one of these tables like this vertically, but as you move through some of your calc classes, sometimes we write them horizontally. I'm going to do that this time. So x and f of x, so it's the same exact idea. Let's pick some numbers around 0. So almost if you think of a number line, right? Think of 0 right here, okay? What are some numbers that get us pretty close? Well, what if we plugged in -1, right? That's relatively close. You could move farther away if you wanted. Maybe your gut said to plug in, -12 or something. That's fine, right? But we could actually plug this in. We can actually get a function value, right? So you would say 1 over -1. You get -1 as an answer. Okay. What about -0.5? These -0.5, right? Well, if I divide that, if I say 1 divided by -0.5, throw it on a calculator to verify this, you actually get a -2. And it's because we're essentially dividing by a fraction, right? So you would flip and actually end up multiplying by the reciprocal, right? Okay. We're closer to 0, right? But there's a whole bunch of decimals who live in between -0.5 and 0 to the point where we get significantly closer, right? So how about -0.1? So 1 over -0.1, again, feel free to verify this on a calculator, you get -10. Okay, can we get closer? 0.01. And this is a common practice you're going to see more and more of, especially as we get into limits and all that good stuff later. Okay, so as you plug this in, 1 over -0.01, you're going to get -100. Can we go one more? -0.001, 1 over -0.001, and you get negative this time 1,000, right? So the question then becomes, I can't actually plug in 0, right? Because I get an undefined answer. We saw that up here. I can't actually plug in 0, but what happens to f of x, and I'm going to say f of x's values as the x values approach x is 0. And this right here, a lot of times we just say, you can say x approaches 0. And I'm going to be really specific when I say that because I'm only currently approaching it from one side, right? Again, thinking on a number line, that's, maybe the advantage to drawing this out horizontally. But thinking on a number line, right now we're approaching from the left. So it's common for us to write x approaches 0 with almost in an exponent's location, a negative sign. Again, just thinking of a number line, right? If 0 lives here, this is the left, so the right would have to be plus. It's just the notation that's common here. So approaching, O-A-C-H, approaching from the right would be x approaches 0 plus. And that's just denoting if we're arriving from one particular side or the other. In this up here, I can say, x approaches 0. You could put the negative up there if you wanted. I do think that's kind of clear because of the numbers we chose, but it never hurts to be extra clear, right? So my question now is, okay, what happens to f of x? Where are these f of x values going as we get closer and closer and closer to this x equals 0 that we can't quite reach, right? Well, we started at -1, and then we went to -2, so it got a little bigger. But then we went to -10, got a bit bigger, and I should say bigger in magnitude, right? So more negative, if that helps. And then it went even more in that direction, right? -100, and then -1000. And to just think about the small space that we covered between -1 and -0.001, that's not a lot of ground that we covered, right? But there's this drastic difference that we're seeing. So think about our visual here, our graph of this function. I'll do the other side in just a minute. But this means even just from -1, our function, we can kind of compare it to what we already know, is doing this. Do you see how that agrees with these f of x values, these y values that we're seeing? So we would say something like f of x approaches, and what direction is it heading in? Well, it's a direction, not so much a number, but I would say this is going in the direction of -infinity. Right? And look at that for a moment. Make sure it seems fair, right? Make sure you agree with it. Pause if you have to. I want to do the same thing, but I want to do it from the other side this time around. So I'm going to set up again, just kind of horizontally here, x and f of x. And I want to pick some values where maybe 0 is here now. And what happens, leave myself a little bit of room. Right, the same thing, x approaches, and we'll put 0 from the right, and we'll see what happens to f of x, right? But what are some values to the right of this? Now, I like mimicking what I did, right, in the previous question. So some symmetry is appreciated. So if I use -0.001, how about +0.001? And we do the same thing, right? The function is exactly the same. We're still working with f of x as 1 over x. So this would be 1 over 0.001. Well, that's 1,000, right? Numbers are the same. It's just different signs. 0.01. 1 over 0.01 would be 100. Again, throw it on a calculator. You can verify it with the previous group we did. How about 0.1? Well, it's 1 over 0.1, and that's 10. 0.5, again, I'm just kind of doing the reverse in the other direction, right? 1 over 0.5 would be 2, and maybe 1, positive 1's time, right? 1 over 1 is 1. So again, as we get closer and closer, and the direction on this changed, right? And the first one, our x values were going this way, trying to approach this purple, this x equals 0 line, right? But what happens as we approach from the right this time, right? So I'm kind of, caving in on this one particular value in the middle. Well, let me get this out of my way so I can graph. Well, what happens this time is, again, we can compare it to what we know about the graph. We're increasing, right? So maybe I draw my line just to show we're caving in on those values or surrounding them. But we can see here, right? 1,000, but then down 100, 10, and 2, and 1. And technically speaking, because the function does go in that direction, right? I should not have drawn that with a highlighter. Technically, f of x moves this way. That's why we see our values decreasing, but that's not really the way I'm measuring it. I'm measuring it as I get closer to 0. Well, as we get closer and closer to 0, you can put 0.0001 and throw as many zeros in there as you want. We're actually increasing this time, and we're going to infinity. Okay, so as we approach from the right, and we kind of put that up in here, right? What we kind of do with these two pieces of information. So these two kind of come together. You can see my purple line up here, but these two kind of come together, and we say f of x increases without bound as x approaches from the right. Yeah. And then on the other side of this is f of x decreases without bound as we approach from the left. And really, when one of these two things happens, this is where we run into domain issues. We're going to tie this in with vertical asymptotes in a little bit from now. But we want to kind of unify these concepts. So again, I know there's a much faster algebra way, but that's not really how we do math, right? Math is kind of learned in reverse. We teach you the quicker approaches, the more, like straightest path to your answer kind of approaches when you're in an algebra class. And then as you get to pre-calculus, calculus, the world beyond, we start to peel away at those more complicated topics. And we now want to talk about, why do they work? How come that shortcut works? Right? How come we can just plug the denominator in and know that that's correct? Well, it's going to tie in with what we're seeing here with domain, as well as what we're going to see with our vertical asymptotes in just a little bit. Okay?